In this video, we'll talk about the reduce and return method of circuit analysis when we have a series parallel circuit. So in this circuit, what we want to do is through a series of steps, we want to reduce this circuit down to just one voltage source and a resistance, a total resistance for the circuit as seen by the voltage source. That way, we'll be able to determine how much current is required from the voltage source in terms of our source current. And from that, we'll step back up and return through those steps to find everything else, our branch currents and our voltage drops. So we're going to use this circuit as our example. And the first step, you want to, I like to start as far away from my source as I possibly can. So I tend to go all the way to the end of the circuit. And what I notice over in this last branch is R3 and R4 are connected right here. And there's nothing else connected between them. So they've got only that one connection between them. What that tells me is the current through R3 has to continue through R4, which makes these two resistors series resistors. Okay, so I would call that RA, and that's going to be R3 plus R4, where we have 12 ohms there. So at this point, we can redraw our circuit. However, I'm going to go ahead and take a second step at the same time. Now, I don't want you to take multiple steps if they involve the same portion of your circuit, but if they're separate portions of the circuit, it's okay, as long as you're not. Because if you do too much to the same portion of the circuit, it's easier to make a mistake or to make a misstep in your calculation. So I also notice that my 10 ohm resistor here and the 15 ohm are connected on the top and they're connected on the bottom, which tells me that those two resistors connected in 2 points are actually in parallel. So I'm going to call that RB, where R1 is in parallel with R2. So to calculate the total resistance there would just be 1 over 10 plus 1 over 15. And that's going to be 6 ohms. So this is going to be RB, and this is going to be RA over here. Sorry, let me just, now I'm going to scroll down and redraw my circuit. Let's see how much of this I can keep on the page at once. Okay. So when I redraw the circuit, I've got my 36 volt source, and then taking the place of R1 and R2 is going to be RB, which equals 6 ohms. And then taking the place of R3 and R4 will be RA, which is 12 ohms. Okay, so this is a simplified version of the previous circuit. So I'm going to label our original circuit number 1, and our second circuit I'm going to label number 2. Now let's see if we can reduce this a little bit further. Notice in our next circuit, and now I'm going to treat this like it's a whole different circuit. We notice that RB and RA are connected on the top here, and they're connected on the bottom. So that tells me that RB and RA connected in 2 points are in parallel. So I'm going to find, and that's going to be my final resistance, which is our total resistance of the circuit, is RB in parallel with RA. 1 over 1/6 plus 1 over 12, and RT must be 4 ohms. So when I redraw the circuit one more time, I now have a 36 volt source and a 4 ohm RT. And I'm going to call that my third circuit. Okay, so what does that tell us? Well, this is where we can now find our source current. So I sub S is going to be E over RT, just like we found for series and for parallel circuits. Separately, when we put them together, the same is true. We have 36 volts we're applying to essentially 4 ohms of resistance. So that means that we're supplying the circuit with 9 amps. And I'm just going to draw that 9 amps right there. And then the voltage drop across RT would be that source current times RT, or 9 amps, times 4 ohms, or 36 volts. So I'm doing that just as a placeholder, but recognize that if you're supplying one resistor with 36 volts of voltage, you'll have to see that voltage drop across RT. That's Kirchhoff's voltage law. The sum of the voltage rises minus the voltage drops in a closed loop has to equal 0. Also, in this case, not only is that resistor in series with the source, it's also in parallel with the source because they're the only two components in the circuit. Okay, so once that's done and I have found all voltages and currents for this third circuit, now I can step back up to the previous circuit and work with it. So I'm going to transfer everything I learned from the third circuit up to my second circuit. I'm not going to go all the way up to the first just yet, but I know that I'm drawing 9 amps of current from that source, so that's not going to change. So I have that 9 amps of current there. And then this 36 volts across the 4 ohm resistor, remember that's across parallel RB and RA. And we know that in parallel, resistors have the same voltage drop. So that 36 volts is what I'll see across each of my resistors, RB and RA, which will allow me to find the current through RB and the current through RA. So IB is what I will call the current through RB. That's going to be the voltage drop across B over the resistance of B, which is 36 volts over my 6 ohms of resistance, or 6 amps. I'm going to give my sink a little time to get there. And I should have 6 amps of current right here through RB. All right, now, then I want to find my current through RA, which is going to be the voltage drop across A, not B, A, divided by the resistance of A. So I've got that same 36 volts drop because it's in parallel with the source as well, over my 12 ohms. And that means I should have 3 amps through my 12 ohm RA up here. Now notice Kirchhoff's current law says that the current coming into the node has to equal the current leaving the node. So we have 9 amps coming in, 6 amps going through RB, and 3 going through RA. So that adds up, and we're ready to move back to our original circuit. It's going to move that up, and we're going to transfer everything we learned up to here. So we know we've got 9 amps of current coming from the source. We also now know that this is 6 amps and that this is 3 amps. That's what we just found. Now, what would be the voltage drops across each of these resistors? Well, remember, R1 and R2, we split in parallel. And we had 36 volts drop across RB. Well, we're going to have the same 36 volts drop across each of these because these resistors are in parallel. And when we combined them, we didn't change that voltage drop. So we're going to have 36 volts across each of those. So how do we find the current through R1 and the current through R2? Remember, the current through R1 is just the voltage drop across R1 divided by R1. So the voltage drop across R1 is 36 volts, and the resistance is 10. So 36 volts divided by 10, 3.6 amps. Okay, so that means we've got 3.6 amps of current here. Now, what about IRB? IR2. Well, that's going to be the voltage drop across R2 divided by R2. So we've got 36 volts across R2 and 15 ohms of resistance. So 36 volts, 15 ohms means that we'll have 2.4 amperes of current here. So 2.4 amps. And again, make sure that makes sense. You've got 6 amps coming into this current divider. 3.6 amps goes to the left, 2.4 to the right. That adds up to 6, so that makes sense. So on the other side, both of those currents will come back together, and we'll have our 6 amps again. Remember, Kirchhoff's current law says the current can come in, do anything through there, and then come out. It has to equal what came in. Okay, so let's move on to let's see. Let me put that back. Let's move on to R3 and R4. So let's find our voltage drops across R3 and R4. We're going to call them V3 and V4. So the voltage drop across R3 is going to be I3 times R3. Again, we're just applying Ohm's law over and over and over again. So the current through R3 is that 3 amps, and the voltage and the resistance is 10 ohms. So we've got 30 volts drop here. And for V4, that's going to be I4 times R4, which, since R3 and R4 are in series, they both have that 3 amps across them. So we're going to have 6 volts there. And remember I said that the series resistors divide the voltage. Well, remember, these two series resistors together are in parallel with the 36 volt source. So they're dividing that voltage into 30 volts across the 10 ohm resistor and 6 volts across the 2 ohm resistor, which is proportional to those resistor values, because the 10 ohm is how many times larger than the 2? It's 5 times larger. Notice it's got 5 times the amount of voltage across it too. And that's what we mean by voltage divider. So now we have solved for everything in our circuit. We know all of the currents through all of the resistors. The only thing we haven't looked at just yet is this VA right here. We're asked for VA. Well, VA, when you see a single subscript notation like this, we're talking about VA minus the voltage at ground. Okay, so with respect to the voltage down here. So what that really means is if I put a voltmeter right here and I put the red lead pointing there, the black lead at ground, what would be the difference in voltage from that point to that point? Well, notice that that's actually in parallel with my R4. So VA in this case would simply be the same thing as V4, which would be 6 volts. So in the next video, we'll work another problem.